Okay, so this is day 3 of our trigonometry unit here. We're going to start to talk about, I know you've heard these words probably before, but talk about what is a sine, a cosine, and a tangent ratio. So just to start, when we're labeling triangles, yeah, we can call a side by the vertices. So this could be AC, but we can also use the lowercase letters, as we've talked about, for the side that's opposite of a certain angle. So if that's big A for an angle, little a's directly across. Big C, little b's across. Big C, little c's across. And then in right angle trigonometry, so that's what we're going to start with here, is triangles always with a right angle. There's another way that we can kind of label those triangles to talk about which side we're talking about. So I'm going to write some definitions down here in just a moment. And so the reference angle, it's always going to be a non-right angle, so an angle that's not 90 degrees, and we'll see why in a moment. But you get to pick which angle you want to be as your reference angle. And that's going to help dictate what your other sides are. So the hypotenuse, that's one that you're familiar with from talking about Pythagorean theorem, is it's always that longest side, or another way to think about it, it's always the side that's across from a right angle. The opposite and the adjacent sides, like these are newer names when we talk about the material in grade 10. So opposite side refers to the side that's going to be opposite of your reference angle. And the adjacent side, you can think about it as it's the side that's not the hypotenuse or the opposite, if that helps, or it's the side that's between the reference angle and the right angle. So we're going to label the triangles based on what reference angle we're choosing. We'll see what that looks like. And so depending on where we pick the right angle, the sides are going to change. So here in this first triangle, again, yeah, you get to pick. So I've chosen B is going to be my RA, my reference angle. And if I do that, well, opposite is always the side across the triangle. Oops, I smudged it. Across the triangle from the reference angle. So this has to be the opposite side. The hypotenuse is directly across from the right angle. Always, always, always. It's always that longest side. And then the adjacent is the other side, or the one that's between the right angle and the reference angle. Now, if I choose a different reference angle, like I did here, A is my reference angle. Now, all of a sudden, this side down here is opposite of that. So I switch the name. Hypotenuse is still across from the right angle, and now the adjacent side becomes this side, my third side, between the reference angle and the right angle. So same triangle, but these two sides can change depending on which angle I choose as my reference angle. So it's very important to know which one are you picking as your reference angle, and we'll see that when we start to look at some examples. Now the issue, if I try to pick this as my reference angle, hypotenuse is across from the right angle, opposite is across from this reference angle, so both sides end up being the hypotenuse. And then adjacent doesn't really make any sense here anymore, where it can't be the other side. There's no side between the reference angle and the right angle, so this triangle here, like, it just doesn't work. It doesn't make sense. And so we don't want to pick the right angle, the 90-degree angle as our reference angle. We always want to pick one of those other two angles for this labeling system to work. And we'll see why we're doing this labeling system in a moment. And so where ratios of sides come in is we've talked a little bit about similar triangles and how the ratios, they don't change at all. So like if you had two triangles that were the same, and excuse my drawing here, I'll give it a right angle at least. but I'm trying to make these similar, be the same shape. If I triple one side length, I have to triple all the other side lengths in order to make it still be the same, I suppose. And so everything gets scaled up, and so those ratios can be helpful to try to find the side lengths of a new triangle, as we know. And so when we talk about these three sides, we can look at the different pairs of ratios that we have. So we can talk about like the ratio of these two sides, the ratio of these two sides, the ratio of these two sides. And we're going to start to look at that here for some triangles that we have on this paper and just see, can we figure out what the ratio of these sides are? So I'm going to write this out in just a moment and come back. So there are two triangles here. And the first question is asking about a 20-degree angle. So 20-degree angle, we're looking at this angle right here. And it's asking about the opposite side and the hypotenuse side. So opposite of the 20 would be, this side right here, my 3.4. The hypotenuse of this triangle is across from the right angle. So it'd be this 10. And so if I do my opposite side, 3.4, divided by my hypotenuse is 10, I get 0.34. And so I can use these labels to help figure out what is the ratio of those sides. And it turns out that because if I tripled everything or I doubled everything, I get that same ratio of sides. The ratios never change. And so our calculators, they actually know these ratios for all these different angles because they don't change. If you have a 20-degree angle in a right angle triangle, that ratio should always be the same because it's just getting scaled up. And so on my calculator, we'll pull out calculator here, there is this SIN button. And if I ask it sine 20, it actually gives me, well, it's not quite exactly what we got because these were maybe approximate numbers, but it gives me about that 0.34, and it actually gives me a little bit more exact number than we had here, but it knew that ratio should be about 0.34. And so I'm going to write out the rest of these ratios here. We're going to talk about what is this thing here. And so we talked about that was our opposite of 20. That was our hypotenuse of 20, which means this should be our adjacent side of 20. So adjacent side divided by the hypotenuse, I can do 9.4 divided by 10. I get 0.94. Opposite over adjacent, so the opposite side divided by this adjacent side gives approximately 0.36. And then for this second set of angles, 70 degrees, we're looking at the same triangle, but now this is the opposite side. So I get 9.4 over my hypotenuse of 10.94. Now this is my adjacent side between the reference angle and the right angle. So I get 0.34. These ones kind of switched the ratios here. And then my opposite over adjacent, because those sides switched as well, I basically just get the reciprocal, which is about 2.76. So that's filling out for this triangle. I'm going to quickly do the same for this triangle here as well. And so here's the filled in table. Again, depending on what is your opposite side, so opposite of 55 was 8.2, opposite of 35 was 5.7. Your ratios are going to change, your adjacent and your opposite sides change, and then this opposite adjacent one, because those sides are changing again, we get a reciprocal, but that should be our filled in table based on those side lengths. And so we're going to talk a little bit more about these ratios here. And so no matter what calculator you're using, you should have these three buttons here. And I know a lot of people say like sin, cos, tan. The words we're going to use are sine, cosine, and tangent. So we tend to say like sine, cos, not cos, sine, not sin, and tan. But those three buttons are talking about these three ratios here. So we give a name to this opposite hypotenuse ratio instead of having to talk about, oh, the ratio of the opposite and hypotenuse sides every single time. We just say the sine ratio. We give it a name. Adjacent over hypotenuse is always called cosine. Opposite over adjacent, that ratio of those two sides is always called tangent. And because for similar triangles, those ratios are the same no matter what your side lengths are. It's just the angles that help tell us the ratios. We can give them names since they are always the same for a certain set of angles. And so it can be a little bit tricky to try to remember, okay, sine, like what two sides do I need to remember to use? So we have a way of remembering that as well that you may have heard before, but I'm going to flip over the page here. So before we quite jump in to the next part, I want to talk about this symbol here. So it's basically a circle with a line through it. Most people kind of write it maybe more like this, like a circle with a straight line through it. When I try to write it quickly, it often looks a little more rounded. Doesn't really matter, but either way, this is a Greek letter. It's called theta, and so we often use Greek letters in like math and science to talk about certain concepts, and just as like that way we're not just using like X's and N's. We have more letters to kind of work with, like pi. Pi is really, it's a Greek letter as well that we use. There's some other Greek letters you're going to come across the next few years. In math and a lot of like physics courses, we just use this as a variable or a placeholder for angles. So it looks new and different. It's called theta with like a TH. I always in high school thought it was feta with an F, kind of like feta cheese. Turns out I've learned a few years into math that once I saw it spelled, that it has a TH. Not really important at all. But you will see this a lot. You might see X as well, but because X get used for so many other things, you often see this used for angles. So if you ever see this symbol, it just means like some angle. It's a placeholder for an angle. And so looking at those ratios we talked about on the other page, we can say that the sine of some angle, like that ratio for a certain angle, let's see, is this gonna focus? There we go. It's always the opposite over the hypotenuse. And so to help remember that, we take the first letters of those three things. So let me move my hand so it focuses, but like S, O, and H. And then cosine was adjacent over hypotenuse, so CAH. Tan is opposite over adjacent, so TOA. And we take all those letters, and if we spell them out, we get this, which we read out as SOHCAHTOA. So you've heard people, like older siblings, or just, I don't know, maybe you've heard that in the past, maybe that's brand new, but SOHCAHTOA, SOHCAHTOA, you'll hear me say it over and over again. It's just a way to help remember all these different ratios off the top of our head. And so it seems like a kind of a random word here, but the hope is that you hear it so often that it helps remember which ratios go with which of these sine, cos, and tan. So I have drawn out two triangles here. And so I've labeled the sides like 1, 2, and then because the numbers don't work out super nice, if I did Pythagorean theorem, I get about 1.732 as that third side. And then I have a scaled up version. So I multiplied everything by 5. So 5, 10, and this side works out to be about 8.660 if we round. But these triangles are similar. They have the same three angles. So 30, this would be 90, and so that would mean that the other side has to be 60. And we can talk about our ratios. So I've written down, so if I look at the sine of both these triangles, so my opposite over hypotenuse, 1/2 gives us 0.5. Or if I look at this triangle, my opposite of 5 over my hypotenuse of 10, that also gives me 0.5. So it doesn't matter what the side lengths are, because everything's scaled up by the same amount. The ratios should always be the same. And I can check that on my calculator if I put in sine of my angle 30. It's going to tell me my ratio of 1/2 or 0.5. So your calculator knows these ratios. I'm going to fill in quickly the rest of this, but yes, all the ratios should be the same. And so with our other sides here, because of these kind of annoying decimals, it doesn't work out quite as clean. But if I do my adjacent and my hypotenuse sides of both triangles and do my division, I get about 0.866, which again, we kind of mentioned, we can call that the cosine ratio or the cos ratio. So if I check cos of 0.866, oh, sorry. Cos of 30 is my angle. I always need the angle with the trig ratio, and that gives me about 0.866. And same thing with my tan ratio, which I originally wasn't thinking and switched my opposite and adjacent sides, but if that's my 30, that's my opposite, that's my adjacent. So 1/1.732 gives me about 0.577, which if I check tan of 30, my calculator agrees that's about 0.577. And so I got the same thing with this second triangle here. And so now that we kind of have established our calculator knows some of these ratios, it becomes very important to know how to use our calculator. And so this is where I maybe remind you that it's really important to get your own calculator, because every single calculator is going to work slightly differently in terms of like the menus and even how you're entering these answers. And so you want one that you can do the same thing on every single time, and you can start to grow your comfort level, because the first thing we need to do is make sure your calculator is in what we call degree mode. And so we measure angles in degrees. We kind of take that for granted because it's the only thing we know, but there is actually other ways to measure angles, and your calculator knows that. So we need to make sure the calculator knows we are measuring our angles in degrees. And so very likely on your calculator somewhere, you might see a D. And let me see if I can quickly change this without going too far into the menus. Maybe I'll use this one as an example here. The other option is maybe you might see like something that says like deg. And so it turns out like there is radians and what we call gradians as well. So it might say deg, rad, and grad, or it might say D, and there's actually right beside, I don't know how well you can see this at all, maybe not, but grayed out there, there's an R and a G. So we always wanted to say D, or we wanted to say deg for degrees. And so this style of calculator, this just switches between the modes here. There's some other calculators that might have like a button that says like mode or setup or something similar. So this one for mode, if I hit it a couple times, I see degrees, radians, gradients. So I want number 1 for degrees, and there it has a D for degrees. This calculator is a little more powerful, so it has more menu options. I want to choose my angle units. I want to choose degrees. And so again, we have D for degrees. So your calculator might not work the same as any of these three. Again, every calculator, the menus are different, but look for a button on your calculator that says something like maybe setup or mode, or you might even have like a DRG button, but something that's going to let you try to make sure your calculator's in degrees. Check with the people around you, see if you can figure out if your calculator's in degrees, and if not, how to change it. But that's your first step. And so the test is, after we talked about this, is that we know, I should have maybe chosen a different angle here, but if you try to calculate, let's say, not cos, let's say sine of 30, that should give you 0.5. And so whether you have a calculator like this, sine of 30, not 300. That gives me 1/2 or 0.5. This style calculator, sine of 30, 0.5. And now this one line calculator, which I kind of said at the beginning, is it's gonna cause you some headaches near the end. You actually have to put things in backwards. You put in your angle first, and then you hit sine, and it tells you 0.5. All right, so just to go back to that. Yeah, this type of calculator with the 2 lines, you can put it in exactly as you see it on paper. Sine 30 equals 0.5. If you try to do the same thing here, if I do sine 30, it just tells me 30 because it hasn't calculated things in the same way. This style of calculator, you have to do it backwards. You have to do 30 and then sine. You might have figured out the same thing. Like if you try to do the square root of 9, you have to do 9 and then the square root. Oh no, you do not have to do that? Maybe. Oh, there, yeah, okay. Let me try that again. So 9 and then the square root of that. And a lot of the things you kind of have to put in backwards. Same thing with trig. And so the further we get into trig, where the equations get more and more complicated, these calculators get more and more annoying. And so this is why at the beginning of the year, I suggested you want to try to get yourself a 2-line calculator, because it makes your life a lot easier, that you can type in exactly what you see instead of having to think how to go about something, how to type it in properly. It just saves you time and a little bit of mental energy. And so there's a little bit of a tangent, but the question might come up where we know a ratio, but we want to check the angle. So far, by doing like the sine of 30, by putting in that angle, we're saying we know the angle, we want to find the ratio. What happens if we want to go backwards here? And so it might help to start thinking about, like, if I know that 4, and so far we've in the calculator we've been putting in angles, and it tells us the ratio back. So we put in like 30 degrees for sine of 30, and it told us that ratio was 1/2. Now, what if we know the ratio and we want the calculator to tell us the angle? And so before we quite talk about that, we'll look at, okay, 4 squared equals 16. We kind of know that's true. We know that's we take that a little bit for granted, but if I rearrange this a little bit, like the left side, I can take the square root, and that helps cancel out the square root and give us 4. And if I do the same thing to the right side, the square root, so I've done the square root on both sides, yeah, we know 4 is the square root of 16. So it's kind of the opposite of a squared is a square root. And so we can talk the same way with sine. There's a way to do the opposite of that. And what that looks like is this symbol. Sine with a -1. It's not an exponent. It doesn't mean sine to the exponent -1. It's just a symbol that we use to basically mean backward sine or the opposite operation of sine, and we call this the sine inverse. So sine inverse of both sides, same as like a square root and a squared cancel out. The sine inverse and a sine will cancel out, and so we can say that 30 degrees is the same as sine inverse of 0.5. And so on your calculator, really close to where there's sine, cos, and tan, if you look, generally it's up above those buttons. Sometimes some calculators will have them as separate buttons, but in the yellow here I have sine to the -1, cos -1, tan -1, so we call that sine inverse, cos inverse, and tan inverse. And so to get those yellow buttons, I can use my yellow shift here. So if I hold shift and press sine, my calculator shows sine -1. And if I type in sine -1 of 0.5, oops, it's going to tell me, well, that's, not minus, equals, that's equal to 30. So sine inverse of 0.5 is equal to 30 degrees. So if I give it a ratio, it knows what angle we should have. And so maybe I can check that here with the 0.866 as well. So that was the cosine. So I can do shift cos gives me the cos inverse of 0.866, which was rounded, but it should give me about pretty close to 30 degrees as well. So if I know a ratio to find that angle, I can use these inverse ratios, we call them, with the -1s. So this example is just evaluate, or that means like calculate these following expressions, and we're going to round to 4 decimal places. And so the first one is, can we just calculate cos of 45? So basically, do you know how to use your calculator to calculate sine, cos, and tan? So cos 45, we get 0.7071. And now I do want you to make sure you get these same answers on your own calculator. And if you're having any trouble, send me an email or ask me in class. But sending an email might be better since we don't come back together until Tuesday next week. And if you do send me an email, let me know what type of calculator you have and I can help. But cos 45 equals 0.7071. And if you use your calculator to calculate these other two, you should get 1.9626 and 0.8290. So just make sure you get those same 3 answers. And then this example, round to the nearest degree. So we're solving for the angles this time, which means we need to do the inverse of our ratio. So the inverse, cos inverse of 0.5 should give you 60 degrees exactly. If you put it in your calculator, don't need to round for that one. And then these two, I've kind of skipped the step of writing the inverse, but you would need to do sine inverse of this decimal. And this one rounds to 60 degrees. And then tan inverse of 1.2345 should give us about 51 degrees if we round. I do have that one still up here. But yeah, tan inverse, we got 50.99. So we can round to the nearest degree, would be 51 degrees. And so with all that being said, we're going to start to get into the meat of this unit a little bit. And so we can use this to solve triangles. And so you've solved for triangle side lengths using Pythagorean theorem in the past, where you know two side lengths in a right triangle. You can use that to find the third. A squared plus b squared equals c squared. But now SOHCAHTOA lets us solve triangles where we only know a side, one side, and then an angle as well. So here, 25 degrees, that's going to be my reference angle. And so this wants us to figure out what is the missing side. So in that case, the missing side here is the b, the little b across from the big B. So it's across from this angle. That's our opposite side that we're trying to figure out. We already know the side across from the right angle, so that's our hypotenuse. And I don't need to know really anything about the adjacent. That's kind of the extra side here. I don't know anything about, and I don't need to find anything about. So the fact that we only are dealing with opposite and hypotenuse is a hint that maybe we should use this sine ratio. And so I'm going to write down that, yeah, sine of our angle is OH, so opposite over hypotenuse. That's our general formula that comes from this SO part of SOHCAHTOA. And so I can sub in things that I know. So we know this angle was 25 degrees. The opposite side we're just calling B. And my hypotenuse was 10. And that gives me an equation for B. Everything else is numbers, so I can try to isolate B here. And so just like we would with, if we knew what this was as a number, B divided by 10, I can get rid of the division by 10 by multiplying by 10. And that's going to cancel out the 10 here. And just leave us with B. And so B should be 10 times sine 25, which we're allowed to write like this, 10 sine 25. So I'll pull out a calculator here. And yeah, you could write 10 times sine 25 or just 10 sine 25. And that's going to give us 4.226. Wants us to round to the nearest one decimal place. So maybe B equals, we can go 4.2. And we'll say centimeters because those were our units up here. So if this side's 10 centimeters and 25 degrees, this should be about 4.2 centimeters, which maybe from the diagram looks reasonable, but don't fall into the trap because often the diagrams are not to scale. But yeah, it should be shorter than 10 for sure. It's a small angle, so probably quite a bit shorter. That looks reasonable. Now this one here with 58 degrees is the only angle we're given. We see across that triangle we have the opposite. I don't know anything about this hypotenuse that's across from the right angle. And then between the reference angle and the right angle would be my adjacent side, and that's the side we're looking for here. So we know opposite, we're looking for adjacent. OA, we can look at tan. So the TOA in SOHCAHTOA, so tan of an angle should be OA opposite over adjacent. And so we'll sub in what we know. I know 58 degrees. I know my opposite is 8. I know my adjacent is side Q, little q. And so now we once again have an equation where we only have one thing we don't know, but this time the thing we don't know is stuck in the bottom of the fraction. And so we could multiply by q to help get rid of the q in the bottom of the fraction, because it's annoying trying to solve for something when it's in a denominator. And we get q times tan 58 equals 8. And now this might be a little bit strange the first time seeing this, but we have q times this. Now if you're in tan 58, that should just be some decimal we get in our calculator. So it's some number, which means if I want to get rid of multiplication, I can divide by that same number. So we're going to divide both sides by tan 58 to cancel out the tan 58 there. And so q is going to be 8 divided by tan 58. And so I can put that in the calculator. 8 divided by tan 58. And we get 4.998, so about 5 centimeters. Now, if you are using a one-line calculator, which again, I highly suggest, spend the $15 and get a two-line calculator, because that's generally all these cost. But if I try to put this in my calculator, I got to go 8 divided by, and I want to do tan 58, so I got to go 58 tan, and that's what tan 58 is equal to. So now to finish the division, I hit equals, and I get that same number here. So the order is quite a bit different, which can be annoying, but it should still be able to work. And so we looked at two examples where we were trying to find a side length. I'm going to look at two quickly here where we're trying to find a missing angle. And so the angle's labeled here. We can call that theta if we want. You could call it capital O if you want. But if this is our angle we're talking about that we're trying to find, we still want to label the triangle. So across from the right angle is going to be our hypotenuse. Opposite, I don't know anything about. And between the right angle and the reference angle is always my adjacent side. And so here, if I have adjacent and hypotenuse, I'm looking at ka in SOHCAHTOA. So we can do cosine of an angle is adjacent over hypotenuse. And so I can sub in what we know. Adjacent is 7, hypotenuse is 13. And just like on the previous page, if I'm trying to find an angle from a ratio, we can do the inverse cos inverse of that ratio, and cos inverse of 7 divided by 13, we get 57.42. So to the nearest degree, we'll do, it's about equal to 57 degrees. And now just to show on this calculator, again, a little more annoying, but I can do my ratio 7 divided by 13. to figure out what that is first in the brackets. And then to get that cos, I need to do this second function button. I get 57.42. So you can still do it on this calculator. It's just the order is different. And then one more here with our angle here with the little asterisks. This side is opposite that angle. This side's between the angle and the right angle, so it's adjacent. So O and A, SOHCAHTOA. I need the tan. And so my opposite over my adjacent, 7/5, is going to be, I could write theta, or you could write this angle E, because that's the angle that we're measuring. And so E is tan inverse of that ratio in order to solve for the angle. And if I do shift tan inverse 7/5, you get 54.46, so we can round that to 54 degrees. So there's a few examples solving for a side length, a few examples solving for an angle. Practice over the weekend, see what that feels like to try some of those questions on your own, because this is a big part of this year and next year in math. And the biggest thing that will help is getting confident with your calculator, because sometimes you understand these concepts, but not 100% sure how to put it in your calculator. So if there's any questions on that, definitely let me know ASAP. Happy practicing over this long weekend.